this. Let's factor. I'm going to factor that. This is called E st times s squared plus 4s plus 3 equals 0. I'm going to stop here for a moment. Or actually on the next one. Next. Okay. So either e to the st has to be 0 or the second factor has to be 0. And without any better knowledge, as far as we know, e to the st is not 0. So let's solve this. So we're going to solve s squared plus 4s plus 3 equals 0. This shouldn't be too difficult. This little piece right here is called the characteristic. Depends on the book. But here that referred to as the characteristic equation. Characteristic equation. Or polynomial. Okay, this one works out kind of nice. I think it factors into an s plus 3 times s plus 1 equals 0. We set each factor to 0 and solve, and we have solutions of minus 3 and minus. Now, I know it's been a while, and all you probably were focused on was the test. So, and that's understandable. So let me remind you what we said. It took us a while, but we said that our null solution is some constant times the first solution. I call it S1 times plus some other constant C2 times e to the S2 times. So there was. So we have a second order equation, there's going to be 2 null solutions. How do you know if those are solutions? Yeah, you can plug them in. You can plug them in one at a time. You can plug it in. You can plug in C1, E, O. But let's write these. Let's let our S1 be the 3 and negative 1 be or the minus 3, S2 be the minus 1. So we can say we have y equals C1 e to the minus 3t plus C2 e to the minus 1t. That would be our solution. So what does this one look like? The graph. I might just leave our graph up here so we can graph a few of these. This one, it starts at some point. Well, you can change it based on your initial conditions. At time is 0, whatever that might be, then you're going to have C1 plus C2 in your initial conditions. So you're going to start at some point here, C1 plus C2, and your graph of this, these are the same thing. This one goes to 0 super fast, and this one goes pretty darn fast. So if you add fast, pretty darn fast, and super fast, the thing is going to 0 pretty quick. And so you get a system, I'm sorry, you get an equation that just comes to 0. And we call this system, this is called over V. over-damped. If you were in a car, it's a pretty stiff ride. I want to do something else. Let's do this. Let's graph the original differential equation. So let's do that. And I'm going to keep track of these. So let's graph. Actually, we're going to graph the characteristic equation. Characteristic equation. Graph the characteristic. Okay. Here's what it's going to look like. Yeah.
On that graph, what is being over-damped referring to?
It's just what we call it. It means that it goes, if you were to hit that speed bump, the car is going to just go wham, and it's going to be, there will be no spring movement. Or the spring movement, remember, that's like a second, and you would be at no spring movement. That's just over-damped.
So what's the line between over-damped and damped?
Critically damped. So, okay. So all forms of damping have a name, an adjective that goes with them. This is over-damped. There's going to be critically damped, and there's going to be under-damped, and there will be undamped. That's just actually, that's a prefix in the last one. But we know none of them are damped. Damped has categories of being damped. Does that make sense? Is that your question?
It makes sense, but that still arises many more questions.
Oh, we'll solve them. Hold tight. Hold tight. Okay. Graph the characteristic equation. I'm going to do that. And what I didn't show you is that if you were to complete the square, I'll do this. Let me just start fresh. That's not fair. Let's do this. So if I had s squared plus 4s plus 3 is some function of s. We'll just do that for right. If I complete the square, this becomes s plus 2 squared minus 1. So in here, complete square. Complete the square. And I'm going to graph that. So we're going to have a couple of those up here. Let's put our graph over here, maybe. So we know that this is a parabola. We know this is a parabola. It's shifted 2 units to the left, and then the vertex goes down 1. So it shifts 2 units to the left. The vertex comes down to 1. Oh, and we even know the roots, don't we? We know the roots. The roots were minus 1 and minus 3. And then continue. So that's our first one. So let's try this again. Let's try this again. Any questions on that? Okay. So notice that if our characteristic equation has, in this case it has 2 real roots, we have 2 real solutions. Next. Okay, wait a minute. So if this one, if this parabola here has two real roots, what if I was to shift my parabola and I started to move it up a little bit? For example, let's say, I'm going to do this all in dotted lines. Let's say I moved it up to right there. Well, then I would have a parabola that would look like this. What would we expect for the characteristic polynomial there? What would we expect of the solutions to it? It would be, you'd again have two real roots. What if I raised it up a little bit more? What would I have? Two real roots. Okay, here's a question for you. If my parabola is over here to the left, I have, in this case, my system is being damped. Meaning it's coming to rest. It's stable. So I'm going to write that. What if my parabola was over here at 1, 2, 3. Oops, those are different. So what if my parabola looked like this? What kind of roots would I have? I have two positive real roots. So if all of a sudden this was a 1 and this was a 3, what would the solution be? Yeah, it would just go poof, like that. Exactly. So this kind of a system, if you have two positive real roots, this is going to be an unstable solution. Unstable solution.
Are these similar to the stable and unstable logistic equations?
Yeah, it's a similar idea. In this case, when we're talking about a stable solution, you have going to 0. A logistic equation either which depended if there's harvest being met. Remember that would go to either 0 or it went to the carrying capacity. But this is the same idea. Some point of rest. Okay, here we go. Let's try that. So, oh, wait a minute. Wait, I remember what I was going to ask you now. What happens if I moved my parabola so that it just rested there? It didn't want to be moved, it just wanted to rest. What would I have there? I'd have one solution. Let's see what that looks like. So let's change our characteristic equation now. Let's do that. So we're going to solve. Solve y double prime plus 4y prime plus 4y equals 0. Let's try again. So what are we going to try? We're going to try y. Try y equals e to the st. Y equals e to the st.
Like the ST, you know that's going to be try other ways that we do our supply. They all work, or we see some don't work.
Some would work. Remember, okay, so did everyone hear her question? So her question, if I was getting it right, was, why are we always trying e to the st? Why aren't we trying something else? So that's actually a great question. And let's take a look at there's that intuition there. Okay? This is your differential equation. And what is it really saying? It's saying that if you have a function that you don't know about, and you have its derivative, and you have its second derivative, what's really happening there is those this function, its derivative, and its second derivative are like terms, meaning they can be combined. For example, if your solution was x cubed, your first derivative would be x squared, your second derivative would have an x. Are those like terms? X squared, and x cubed? No, those aren't like terms. There's no way you can add those three terms to become 0. So, in other words, you have to stick with some function that creates itself as its own like term. That's kind of the amazing part of E. It's the only function out there that is its own like term. What?
Isn't zero somewhere?
Yeah, zeros. Yeah, that's a pretty uninteresting solution. But you're right. 0 does have, you're right.
So why not do 0?
Yeah, we're done. Y equals 0, class is closed. You know, at Stanford, do you hear what's happened with the coronavirus?
Yes.
So Stanford, classes were canceled through the end of March, I believe is what it was.
It's online now,
Yeah, and well, now they're just saying, well, yeah, you can do some kind of online component. And the final exams are all take-home.
It's not even
I know. Can you imagine that? You're like, I have a discussion, I post it, you guys send me your file, we're all done by the end of March. Great. I know.
It's gonna get lower.
I know. Yeah, I don't know why March is going to be coronavirus. I just thought it sounded cool. Man, take. All right, let's